In the farthest reaches of our solar system, beyond Neptune's orbit, something unusual is happening. A mysterious force seems to be pushing around icy bodies, and groups of these objects follow strange orbits that cannot be explained by the known planets alone. Scientists believe this could be caused by a massive, hidden planet, often referred to as Planet 9. First proposed in 2016, this potential new planet has captured the imagination of astronomers. This isn't the first time that a planet has been predicted based on scientific reasoning. The discovery of Neptune and Pluto followed similar patterns. Their gravitational effects were predicted before they were actually observed through telescopes. Astronomers noticed anomalies in the orbits of Uranus, and later Pluto, which eventually led to their discovery. This pattern of using mathematical predictions to reveal hidden planets has led to the hypothesis of Planet 9. Planet 9 is believed to be a rogue planet, possibly captured by the Sun's gravity, or it could have formed from the same disk of gas and dust as the other planets. If it exists, Planet 9 is thought to be at least 10 times as massive as Earth and orbit the Sun at a distance of 400 to 800 astronomical units, AU. 400 to 800 times the distance between Earth and the Sun. Astronomers have been diligently searching for signs of Planet 9 using powerful telescopes and advanced computer models to track its gravitational effects. After years of studying the sky, analyzing data, and running simulations, they now have the strongest evidence yet that Planet 9 exists, presenting an exciting new chapter in the search for hidden planets. So, what proof have they uncovered in their quest for Planet 9? With the ability to detect exoplanets many trillions of miles away, why has it been so difficult to spot Planet 9, which is much closer within our own solar system, even with the most powerful telescopes available? The story of Planet 9 begins long before 2016, shortly after the discovery of Uranus in 1781. Over time, astronomers noticed something strange. Uranus wasn't moving exactly as expected. Its orbit seemed to speed up and slow down, suggesting the influence of an unknown force. In the 1840s, two mathematicians, Urbain Le Verrier in France and John Couch-Adams in Britain, independently proposed that these irregularities in Uranus' orbit could be due to the gravitational pull of an unseen planet. They used complex mathematics to predict where this hidden planet might be located. Le Verrier sent his predictions to Johann Gottfried Galle, an astronomer at the Berlin Observatory. On the night of September 23, 1846, Galle and his assistant pointed their telescope to the exact area Le Verrier had predicted, and astonishingly, they discovered Neptune on their first night of observation. This was the first time a planet had been discovered through mathematical prediction rather than by chance observation. Following the discovery of Neptune in 1846, astronomers believed they had a complete understanding of the major planets in our solar system. However, as they studied Neptune's orbit, they found that, like Uranus before it, Neptune showed slight deviations from its expected path. These small but consistent anomalies led astronomers to wonder if there might be another, as yet undiscovered planet farther out. This inquiry eventually led to the discovery of Pluto in 1930 by Clyde Tombaugh, a young astronomer at the Lowell Observatory. Pluto was initially thought to be the long-sought Planet X, but it was later found to be much smaller than anticipated. Its mass was insufficient to explain the gravitational anomalies observed in the orbits of Uranus and Neptune, suggesting that something more massive existed beyond Neptune's orbit. In 1951, Dutch-American astronomer Gerard Kuiper predicted the existence of not just one, but several icy objects beyond Neptune's orbit. Pluto turned out to be part of a larger region now known as the Kuiper Belt. The first direct observational evidence of Kuiper Belt objects, KBOs, came in 1992, when astronomers David Jewitt and Jane Liu discovered 1992 QB1, a small icy body beyond Neptune. This confirmed the existence of a population of objects in this region. As more KBOs were discovered, the term trans-Neptunian objects, TNOs, was introduced to describe any small body in the solar system that orbits the Sun at a greater average distance than Neptune. These objects have contributed significantly to our understanding of the outer reaches of the solar system. In 2003, the discovery of Sedna, a large TNO with an unusually elliptical orbit, fueled further interest. Sedna's orbit takes it as far as $936 Australian from the Sun, far beyond the known planets. Over the years, more TNOs have been discovered, and one particularly odd feature of their orbits has intrigued astronomers. Instead of being randomly scattered, the orbits of many of these objects appear to be clustered in a specific region of the sky, which is highly unusual. This suggests that some unknown factor is influencing their trajectories. If TNOs were moving randomly, their orbits would be spread out in all directions, much like marbles scattered on a flat surface. However, their perihelion points, where the objects come closest to the Sun, are grouped together in a certain part of the sky, indicating a common force acting on them. This clustering is a significant anomaly, and it has led scientists to hypothesize that there may be a hidden planet exerting gravitational influence on these distant objects. In conclusion, as astronomers continue to study the outer reaches of our solar system and the strange behavior of trans-Neptunian objects, the search for Planet 9 grows more compelling. Whether it is a rogue planet captured by the Sun's gravity or one that formed alongside the other planets, the evidence continues to mount, suggesting that a hidden world nearest and farthest points from the Sun appears to be uniquely arranged in a way that it is highly unlikely to happen by chance. This alignment supports the theory that an external force, potentially the gravitational pull of a large, unseen planet, may be influencing the orbital paths of these distant objects. This provides strong evidence for the hypothesis that Planet 9 could be exerting its influence from afar, shaping the orbits of these far-off bodies. Building on the discoveries of Sedna and other trans-Neptunian objects, TNOs, the theory of a distant, unseen Planet 9 gained significant momentum. In January 2016, astronomers Konstantin Batygin and Mike Brown published a groundbreaking paper that reinforced this hypothesis. They analyzed the orbits of 6 distant TNOs and suggested that the observed orbital patterns could be explained by the gravitational effects of an unknown planet. They proposed that this hypothetical Planet 9 would be about 10 times the mass of Earth and would orbit the Sun in a highly elliptical path, ranging from 400 to 800 astronomical units away. The discovery of Neptune worked remarkably fast, as astronomers found it on the very first night of their search based on predictions. However, the hunt for Planet 9 has proven to be much more challenging. There are 4 main obstacles in locating Planet 9. The first is its distance. Planet 9 is believed to be 10 to 20 times farther from Earth than Pluto, meaning it receives very little sunlight, making it nearly invisible against the backdrop of stars and difficult to detect with current telescopes. The second issue is the planet's highly elliptical orbit, meaning it could spend most of its time in the farthest, darkest parts of its orbit, making it even fainter and harder to spot. The third issue is the vast area of the sky where Planet 9 could be located, requiring astronomers to carefully survey large regions, frequently reassessing and rechecking observations to ensure nothing is missed. Lastly, the planet's slow movement across the sky complicates detection. Due to its immense distance from the Sun, Planet 9 moves slowly relative to the background stars, meaning astronomers must conduct repeated and prolonged observations to track its motion and confirm it is not just a fixed star. To overcome these challenges, simulations have become an essential tool in the search for Planet 9. Simulations allow researchers to model complex systems and predict behaviors that are hard or impossible to observe directly. Let's examine how researchers use simulations to gather the most compelling statistical evidence for Planet 9's existence. The orbits of TNOs are not stable over long periods. Neptune's gravitational influence can alter their trajectories, scattering them or even ejecting them from the solar system. This dynamic suggests that TNOs are continuously influenced by external forces, driving them into orbits that intersect with Neptune's. To explore this further, a research team conducted simulations based on the assumed conditions for the formation of the solar system's outer reaches, particularly the Oort cloud. The Oort cloud is believed to be a distant spherical shell of icy bodies that orbits the Sun from about 2,000 to 100,000 astronomical units away. The team selected TNOs with perihelion distances greater than 30 astronomical units and semi-major axes ranging from 100 to 5,000 astronomical units, resulting in simulations of 10,000 particles. The team ran 2 sets of simulations, one including the hypothesized Planet 9 and its predicted location, and another without it. The results showed that Planet 9 could affect the orbits of TNOs by directly coupling with their orbital dynamics. This coupling alters the shape and orientation of the TNO's orbits. The simulations demonstrated that, in the absence of Planet 9, fewer TNOs came close to Neptune. In contrast, when Planet 9 was included, more TNOs passed close to Neptune, with a number of close encounters increasing over a broader range of distances, starting around 16 astronomical units. To validate their findings, the team conducted a statistical analysis comparing the patterns observed in the simulations with actual observational data. They considered potential observational biases and compared their simulated results with 17 known TNOs that have perihelia under 30 astronomical units and semi-major axes greater than 100 astronomical units. The analysis strongly supported the model with Planet 9, showing a higher probability of 0.41, compared to just 0.34 for the model without Planet 9. This significant difference in probabilities suggests that the model with Planet 9 aligns more closely with the observed behaviors of TNOs, indicating a potential role for Planet 9 in shaping their orbits. In the near future, the Vera C. Rubin Observatory in Chile will begin operations with a powerful 8.4-meter telescope capable of conducting all-sky surveys. This observatory will use data from ongoing studies, including those suggesting the presence of Planet 9, to closely monitor the movements of distant TNOs. If these TNOs consistently show patterns of approaching the Sun beyond 16 astronomical units, as the Planet 9 model predicts, it could serve as a key indicator of the planet's existence. This combination of cutting-edge technology and groundbreaking research could significantly advance our understanding of the outer regions of the solar system and potentially lead to the long-awaited confirmation of Planet 9. Recently, the James Webb Space Telescope has measured the rate at which the universe is expanding. The results have revealed a major crisis in cosmology, indicating that there is a fundamental flaw in our current understanding of the universe. If you missed this revelation, be sure to catch up with this incredible discovery. If you learned something new from this video, please remember to like it and subscribe to our channel for more updates. See you in the next one.